I'll turn it back, kind of same bio as you had before. So I'll just kind of turn it back over to you, Jerry, and
Okay.
you should be good to share your screen and good to go. So tonight's
All right.
part 2 of errors and measurement errors, behaviors, and analysis. So
Okay, I think this is the one. Yeah, screen 1. Okay, share. So everybody should see my PowerPoint up there. Okay.
yep, you're good now.
All right. We're gonna kind of pick up where we left off last time. And we burned through a lot of material really quickly. And again, I want people to understand that this is, again, just to bring you up to speed on the concepts of errors. It's not to necessarily make you experts in it, but to understand that whatever we do, there's going to be errors in all of our measurements. We kind of went through some of the basic definitions last time. I stopped right at the error propagation. And error propagation is where we take the behavior of individual errors, individual random errors, and we combine them with other numbers that have random errors. And then we come up with a result. And how do those random errors affect those results when we get done computing or manipulating them and that type of thing? And when we talk about propagation, there are a lot of different ways that errors can propagate depending on how the numbers are combined. But some of the more common ones, and we see these as recurring themes in surveying, is one is an error of a sum. Error of a sum, it comes into play whenever we're adding together numbers or subtracting numbers for that matter that are subject to errors, and we come up with an answer. The question is how those individual errors contribute to that answer. So in this case here, the example I've got, and this is just to show you it's not a surveying type thing, it's any measurement science is subject to these types of errors of propagation. We've got a soil sample that's divided into 3 parts and they're weighed independently of each other. And there's an uncertainty in the weights of those individual parts. So the question is, when we add up the most probable value of these individual ones, we get 127.6 grams for the total weight. The question is how do these errors propagate into that answer? And most people would say, well, we're going to add them together, say 0.15 plus 0.21 plus 0.11, and express that as the uncertainty in the total or in the sum. Well, the problem with that is that presumes all the errors are acting exactly the same way. If we're adding 0.15 and 0.21 and 0.11, we're expecting that in all cases, the error is going to be at the maximum. Well, it might be 0.15 positive for the first one, but it might be negative 0.21 for the second one. It could be 0 for the third one because it's a range of numbers. And the way errors propagate, whenever we're dealing with probability and statistics, is we always get the square root function in there. We're squaring things and taking the square roots of things. So the individual errors squared, we add those up and take the square root of that, and that is what the resulting error is going to be in our sum or in our subtraction. So in this case here, we take the individual errors, square them, add them together, take the square root of them. So our uncertainty in this total error weight, excuse me, is going to be 0.28 grams. So it's somewhere, within the range of all these acting together. Now we'll revisit this one here when we talk a bit more complex relationships a little bit later on. One that we use a lot in surveying is the error of a series. An error of a series is a special case situation of the error of a sum, and it assumes that all the individual errors are the same. For instance, if we've got, every time we set up a differential or an automatic level, we determine an elevation difference. If we can determine that to within a certain uncertainty, then we can project what our total error is going to be on a level circuit that we run. And the way the error accumulates is that the error itself times the square root of the number of chances it gets to occur. And we see this all the time in level loop adjustment. If you look at the FGCS specifications for a geodetic leveling, and they give loop misclosures or link misclosures, it's always in terms of a constant times the square root of something. Well, in this case here, if this crew can determine elevation differences within an uncertainty of 0.015 feet every time they set up the instrument, then if they set it up 4 times, we expect their misclosure on that circuit to be plus or minus 0.03 feet. So because the error accumulates, it's the same error accumulating repeatedly, we just take it times the square root of the number of chances it gets to occur. Now, another simple one, we don't use this one too much. We start to kind of wander off based on most mathematical relationships, but another one that just kind of demonstrate how these errors behave as a square root of the sum of squares is when we're multiplying or dividing numbers, and each of those numbers is subject to an uncertainty. So in this case here, let's say that we've got A with an uncertainty, B with an uncertainty. If we multiply A times B, what's the uncertainty in that product? Well, the error of a product says is the one number times the error on the second number squared plus the second number times the error in the first number squared. It's kind of a cross multiplication type of thing. And if you think about it, it makes sense. If I look at the area of a rectangle, if I have an uncertainty in here of 0.83 feet, then when I figure out the area of this thing, it's going to be uncertain in this direction and in this direction. It's going to be a product type of situation. But again, because it's positive or negative, we can't just say, well, we'll take this uncertainty times this uncertainty and say that's the uncertainty in the product. So in this case here, if we compute the area, it's 18,200 square feet. And if we look at significant figure wise, this has got 3 significant figures and this has got 4, the answer is going to be good to 3 significant figures. So if we just deal it strictly on a significant figure basis, it's good to the nearest 100 square feet. But if we actually propagate the error based on the actual uncertainty in these numbers, if we take this times this error squared plus this times this error squared and take the square root of it, we get plus or minus 130 square feet. Now that's compatible with this, but it tells us instead of being good to plus or minus 100 square feet, is actually good to plus or minus 130 square feet. Because now instead of just dealing with significant figures, we're dealing with uncertainty in those significant figures based on repeated measurements. So again, that's on random errors. Now, when we want to combine these into a little bit more complex relationships, we get things like this. If we have a distance that we're measuring with a total station, and if we look at the specifications for a total station, it'll tell us that the manufacturer stated accuracy is something like plus or minus a constant plus a part per million. So for instance, I might have a total station that says the manufacturer stated accuracy of the distance is plus or minus 3 millimeters plus 3 parts per million. So there's a constant part that regardless of how long distances that I measure, there's going to be a constant uncertainty in that of at least plus or minus 3 millimeters as a resolution. The other part is a proportional part. And in longer distances, that becomes a greater contributor. In shorter distances, it's not much of a contributor. But there are other errors that affect the quality of that distance. Think of that primarily as being the resolution ability of the total station to determine the distance. But we still have an uncertainty in the instrument itself when we set it up over the point, and we have an uncertainty when we set up the reflector over a point. Now, this doesn't matter if we're talking about a robotic total station or a traditional total station, there's an uncertainty in setup at both ends. So what we want to know is not the uncertainty between the instrument and the reflector. What we want to know is the uncertainty between the ground point here and the ground point here. And that's a function of the manufacturer stated accuracy plus the instrument uncertainty and the uncertainty of the reflector setup. So this, if you look at it, is the error of a sum because it's the error here plus this constant error, plus this proportional error, plus this error here. We square each one of those, add them together and take the square root of them. So it's simply an extension of the error of a sum. Now, to do that, let's say that we've got a TSI setup error with 5 thousandths of a foot. And we've got a handheld reflector at the other end. The setting is a hundredth of a foot. And we measure a 712.36-foot distance with a manufacturer stated accuracy instrument plus 3 millimeters plus 3 parts per million. Okay. Rather than do all those computations here, I've cleverly designed a spreadsheet. Everybody see that spreadsheet there? That show up? Okay. So that basically it's solving this equation right here based on the 3 millimeter constant for the manufacturer state, actually 3 parts per million, the total station centering error, the reflector centering error, and the distance. And I can see that my uncertainty in that distance is 0.015 feet. So 1/10.5 of a foot. Now, if I were to have a better accuracy or a higher grade instrument, say maybe a 2 millimeter and with a 2 parts per million, we can see that drops it, but it doesn't drop it a whole lot. It's not so much the instrument that's causing us the uncertainty, the largest part of the uncertainty. It's the uncertainty of the setting up and that type of thing. So if I go back to my 3 and 3, and now instead of having a reflector held with a from somebody holding it trying to balance the bubble, if instead we put it on a bipod so that it's more secure, let's say that we can maybe get that down to 0.005. You can see we start to make a difference in here now. Now, if that's not accurate enough for us for the particular distances that we're shooting, then we're kind of limited to what we can do. We can either try to set up more accurately, or we'd have to go with a higher accuracy instrument. So again, it's not just the manufacturer stated accuracy of the instrument that's important. It's also how well we can set that up. All right. So that's how distances, how errors propagate into distances. And this is true also for GPS, because all the GPSs, when you do a horizontal distance, is basically a high-tech version of a total station. So if we look at, and we can break it into 2 components. We have the horizontal component, which is the 2-dimensional vector XY, and then the vertical component, which is the elevation. And the reason we can break that up is because we have different specifications for the accuracy of the instrument in those 2 different dimensions. So if we look at, and this is for, I can't remember offhand which instrument. I think this is one of the Trimble receivers I grabbed it for. But if we look at real-time kinematic with a baseline that's less than 30 kilometers, we can see that our horizontal is 8 millimeters plus 1 part per million for the manufacturer stated accuracy. For the vertical, it's 15 millimeters plus 1 part per million. And we can see that typically we're weaker in that vertical because of the geometry of the intersecting signals and all that kind of neat stuff. So basically, we've got the same thing here. Instead of having a total station setup, we've got a base setup error. If we're using our own base, how well can we set that up over a point? And then at the other end, we've got the rover centering error. And if that rover is on top of a 2-meter rod, and our bubble's a little bit out of adjustment or trying to hold that in the wind, we can have a substantial amount of centering error here. So even though we may have good manufacturer stated actually in between them, it's still a function of how well we can set up the instruments at both ends. Vertical, same type of thing, is how well can we determine the height of our instrument here above the ground, and how high can we determine it here, which is one of the reasons we use fixed height rods now, because that puts us at a fixed height, which gives us a better accuracy on that type of thing. One of the interesting things though is if you use a topo shoe at the bottom of this as opposed to a regular point, does that change the height of your instrument then? Because topo shoes and points and pointed shoes aren't necessarily the same height. So again, there are a couple of other things that come into play, but that goes into the uncertainty in a vertical location. So again, we can propagate that error in a more complex method into those types of measurements. All right, what about angles? Angles are a lot of fun because with distances, you've only got the reflector at one end and the instrument at the other, or a base and a rover for GPS and that type of thing. But for angle propagation, we've got other things that come into play because you have a backside point, you have a foresight point, you have a centering error at the foresight, centering error at the backside, you have the resolution of the total station. You know that the further, the longer your sights are, the less pointing error that you have, the shorter the sights are, the more the pointing errors, all sorts of things come into play. So when we start to take this stuff into account, we start to look at individual pieces and we put them all together. First of all, there's the TSI, the total station point and reading error, and that's going to be a function of two things. The specifications for the instrument, which is again basically manufacturer's stated accuracy based on ISO or DIN standards. And again, remember that doesn't necessarily correspond to the resolution of the instrument and the number of times we turn an angle, because we know that the more times we turn an angle or measure something, the greater chance we give for random errors to compensate and to minimize. So that's from on the TSI side. The TSI centering error is a function of the error of centering the instrument itself. How well can we set up over a point, and the distances to the back sight and the foresight, and the distance between the back sight and the foresight points. And this in here is in there to convert angles to degrees, or to convert distances to angles so that we can be compatible with an angular expression at the end. And then the target centering, which has to do with how well can we center the targets at both ends there. So basically we have three sources of random errors in there that behave depending on their particular situations. And then we take and add them together. Here's our error of the sum again. We square each one, add them together, and take the square root. All right, so now this one's even more of a pain in the butt to calculate than the distance one. So again, turning to my spreadsheet, say we've got a total station with a DIN spec of 2 seconds, centering error of 0.05 feet that we can set up over the point. Backside and foresight centering errors, let's say for the backside, we've got 0.005 feet here because we've got it set up on a tripod. Over here, we've got maybe a handheld prism or handheld prism pole. We got these respective distances, and the angle is measured 2 direct and 2 reverse to get 123 degrees, 30 minutes and 10 seconds. So what's the expected error in that angle? All right, so using all that stuff, here's our 2 seconds, our 2 direct and reverse. Here's the angle that we turned. The total station centering error, the distance to the backside and the foresight, and the backside and the foresight's centering errors. So at the instrument, because we only turn 2 direct and reverse, our pointing and resolution error at the instrument's 2 seconds, the DIN standard. At our centering errors for our for our instrument and our backside and foresight distances, we got 4.5 seconds there. And for our target sighting errors, we got 7.5 there, for a total of this squared plus this squared plus this squared, the square root of 8.7 seconds. So in that angle, there's an 8.7 second uncertainty using an instrument that's got a 2-second DIN standard accuracy. So we're thinking, well, we paid all this money for a highly accurate instrument like that. Why is it 8.7 or 9 seconds? Well, it's because it's not just the instrument resolution that comes into play. If we'd have turned say 3 direct and reverse sets, it drops down a little bit. If we'd have turned 4 direct and reverse sets, it drops down a little bit more. But you can see that the more times we turn, the smaller that error becomes. If we only turn 1 direct and reverse set, we've got 10 seconds in there. So again, at some point, there's a point of diminishing returns. How accurate do we need the angle to be? If it needs to be more accurate than 2 direct and 2 reverse, giving us 9 seconds, what can we do to increase that error or to decrease that error? As a matter of fact, I think that 0.01, my foresight centering error is 0.01. So 0.01, it's 11.4 seconds. If I were to put that on a tripod, make it the same as that forward one right there, I eliminate 3 seconds of error and stuff. So again, you got to kind of look at it as a system. And when we talk about least square software, you put in a lot of information about what are your expected errors and your angles, your setups, and all that kind of stuff. It takes all that into account when it does the adjustment and weighs things accordingly. All right, get that out of the way. All right, so what it boils down to is the surveyor is an error budget manager. Part of what you're doing is you're not just out there measuring things, you're out there trying to control the situation so that you can minimize the amount of errors that you have to deal with, because it's going to have an effect on the answers you're going to come up with at the end. Ultimately, when the client says, what's my area, and you want to be able to express it to a reasonable level of accuracy based on what your measurements tell you. So we can eliminate mistakes, remember, by repeating measurements and finding where we're outside of a range or outside of a tolerance. Systematic errors, we saw that we use procedure, adjustment, computation, or combination to compensate for that. But once we eliminate all that stuff, then what we got left are random errors. And the way to minimize random errors is to use the appropriate equipment with knowledgeable personnel with careful measuring techniques. So if we need something more accurate than that 11 seconds that we had for the angular error, what can we do to lower that? Do we have to go to a different instrument, or can we repeat measurements, or can we change our target centering errors by using a better setup type of thing? So we got to kind of take all that stuff into account, and that comes with experience. That's one of the problems that students have when they first start learning surveying, is learning the processes that help them control the errors. So that when they do get a good traverse closure, they get it by design, not by accident. You know, that's what you don't want to have something occur because, you know, keep your eyes closed and hope it turns out real well when you get to the end there. All right. There's a couple of chat things there. Angles more. Yeah, it is more than I thought. And I do have that spreadsheet set up on my webpage. You can download it, play around with the numbers on your own a little bit, just to see what some of the effects are and that type of thing.
Yeah, I threw that in the chat there, Jerry.
Okay.
And then I will say, so I used to work for a local power company. We had to do 16 sets. And so I took your 2 versus my 16, and it only picked up like 1 second.
Yeah. And again, if you look at the FGCS specifications I showed last week for turning angles, you know, for a triangulation network and that type of thing. First order, you had class 1, first order, you had 16 direct and reverse. Third order, you had 2 direct and reverse. You know, so exactly. it does make a difference, and the resolution of the equipment that you're dealing with.
What about have you done a spreadsheet for the GPS observations? I saw you.
No, I haven't. But okay. For the horizontal component, you can just use a distance one. And the vertical one, I could put together something relatively quickly with respect to that.
Okay, yeah, just
maybe I'll do that. Put that together, because I'm always looking for stuff to do because I have so much time on my hands.
Exactly.
Okay.
All right. Thanks.
All right. Least squares adjustment. Least squares, well, we know that the term least squares comes from the fact that when we come up with an answer based on repeated measurements, it's the answer that minimizes the sum of the squares of the residuals. That's the one that's most statistically significant, or the strongest solution to a measurement set. Whether we're doing unweighted measurements, that is, we're treating all the measurements the same, or if we're dealing with weighted measurements. And we saw an example of that last time, where we mixed different weights of distances together and then used them together and came up with a weighted most probable value. The primary advantages to least squares adjustment is it models random errors better. Ultimately, when we have errors that are in the system, whether it's a level loop misclosure or traverse misclosure or whatever, we want to take that misclosure and we want to distribute it back into our measurements. And the way we'd like to distribute that back into our measurements is a way that models or behaves the same way the errors accumulated. And we're able to deal with multiple unknowns simultaneously. It's sort of like multitasking on a grand level with respect to dealing with multiple unknowns. It's easy to incorporate redundant measurements. As a matter of fact, the more the merrier. The more redundancy we can put into the network, the stronger it becomes, and the easier it becomes to do quality control to determine where our problems are. And we can easily use mixed quality measurements. And that's where we get into this weighting criteria and stuff. And it can generate all sorts of statistics. It can generate statistics for the overall adjustment that kind of gives us an idea of how well is our adjustment with respect to itself. You'll hear terms, and I'm not going to deal with this too much tonight, but constrained and minimally constrained adjustments. A minimally constrained adjustment, you generally run that to make sure that the data fits well with respect to each other before you force it to fit within a control network and that type of thing. But you can generate the statistics for the overall adjustment to find out how strong it is. And then once we do get adjusted elevations or coordinates or whatever, we can wind up with uncertainties that we can assign to that based on those repetitions of measurements and that type of thing. The disadvantages are, and you'll see this real soon when I go through a couple of examples here, it's very computation intensive. It's extremely computational intensive. And prior to the introduction of computers, it was almost impossible to do a really thorough least squares adjustment. Not impossible, but very difficult. When we talk about the North American datum of 27, when that was created back in 27 and completed in 1929, there were 27,000 control points in the network, and with 2 unknowns for each point, that means there were 54,000 unknown positions in the network that had to be adjusted simultaneously. So to simultaneously solve 54,000 equations in 1927 technology terms is not that simple to do. So they had to come up with a couple of innovative approaches on how to break that up in that. But it is very computationally intensive. And there's statistics overload. While it can generate statistics, there's all sorts of statistics it can generate, some that make sense and some that don't. And you have to work with it to a large extent to figure out what's going on with some of the statistics. And it's easy to misuse, particularly since we're dealing with software. You can shove things into least squares adjustment that shouldn't be part of the adjustment. And depending on the sophistication of the software that you're dealing with, it may just go ahead and adjust things blindly and not warn you that something's not right. So it is easy to misuse or to abuse it. Now, we talk about least squares. It comes into play with the more redundancies we add to the network, to whatever that we're measuring, the more least squares becomes the appropriate solution for it, or in some cases, the only solution to resolve the unknowns. Now, if we start with a simple level circuit that runs from BMA through Q through to T back to BMD, we can do a simple network adjustment. We've all done this. As we go to point B, the benchmark at D, and we see we got a misclosure of 3/100ths of a foot. We're 3/100ths of a foot too high, so we're going to subtract a part of that 3/100ths of a foot from each one. So since 3 elevations were established, Q, T, and the closing elevation on benchmark D, we just subtract one of those from Q, one of them from T, and one of them from D, and everything comes real nice. And there's our adjusted network. We've taken that misclosure and we've adjusted it out. That's a real simple way to do it. The problem is that we're treating random errors systematically. And we know that's not how random errors behave. They don't behave in a systematic fashion. They're likely to be positive or negative. So we're assuming that all the elevations wound up to be too high because the closing elevation wound up to be too high. So we gave a part of that correction to each one of these here. Well, Q might have been too low, T might have been too high, and this one might have been too high because that's the way random errors behave. But with a simple network with minimum redundancy, we don't have enough information to figure that out. So we use some sort of simple adjustment to do that. If we add another observation in, say we run a circuit from, we run a line from D back to Q, then we have 2 raw elevations for point Q, one coming through this way and one coming through this way. So I have 2 elevations on it. Now we can still do a simplified adjustment on here, but the thing we got to be careful of is that when we wind up with an adjusted elevation at Q, that we have the same elevation for it both ways. This one accumulated less error, but this one accumulated its amount of error coming this way. This one accumulated its amount of error coming this way. And point T is dependent on this point Q's elevation coming in from this direction, but it's not dependent on this one here. So you can see that when we start to add redundancies, it becomes more complex. If I throw in one more there, going from BMA to T, I've got another situation where I've got multiple elevations at both of these points here, and I have to adjust it in some fashion that winds up distributing the misclosure, and we wind up with a single elevation here. Now, when we say misclosure here, it makes even less sense. Back over here, when we had just this simple circuit here, we had a misclosure. But in here, what constitutes a misclosure? Because when we go from here to here, we're not closing on anything. When we go from here to here, we're not closing on anything. When we go through here, we are closing. So a misclosure is kind of, doesn't really make a lot of sense when you put a lot of redundancies into the network. So we got to figure out some way to be able to do that. Now, what's really, really important, and this is where least squares can be misused or can be applied incorrectly, is that it's only for random errors. Mistakes and systematic errors must be eliminated or compensated. Otherwise, least squares will do a very efficient job of potentially spreading those unresolved errors through the entire network and affecting all sorts of stuff. So say, for instance, I have a level circuit that's got 2 points in it, 2 unknowns in it, and I connect it to 4 benchmarks. And if I've got a bust in this line from here to here, say they forgot to extend the rod all the way or whatever, so I wound up with a bad elevation difference going from this benchmark to here. Well, point Q and all the lines that touch point Q are going to be affected by that. Because in essence, I'm taking the average and including in the average one bad reading. So I'm taking that bad reading, I'm spreading it through all of them. Point R is not affected because point R isn't connected to point Q, so it's not subject to that error right there. But if I run a connection between R and Q, I add that redundant measurement in there. Now, all the lines that touch point Q are going to be affected, including this one here. And because there's a connection between Q and R, that's going to affect the elevation of R, and that's going to affect the residuals in these 2 lines right in here. So I can take that one error and I can spread it through my entire network. Most software, whether it's standalone adjustment software or part of a mapping package or other type of surveying package, will have some degree of blunder detection in it. And what blunder detection does is it goes through and it tries out different combinations of these measurements to see if it comes up with some really off the wall type of answers for elevations of points. And if it finds it, it flags them and it tries to isolate them and say, look, it looks like there's a problem with some of these readings coming into point Q, because if I try these different combinations here, if I go from BMA to R to Q this way, I get one elevation, I get a consistent elevation this way, but when I come up through here, I get an inconsistent elevation. So the blunder detection can help us track that down, although it's not always a clean one, depending on how many unknowns there are and how many connections there are. But the more the degrees of freedom, the harder it becomes to track down those mistakes. All right, the residual sizes and errors for systematic errors depend on how that systematic error behaves. And a really good example of this is a real common one that happens, particularly with students that are first starting to do measurements with total stations on traverses and that, is they forget to put in the correct temperature and pressure in the instrument. And they run their entire traverse with the wrong parts per million correction for all their distances. Well, that's a multiplier. Okay, each of the distances are affected by a scale. On the other hand, if they put in the prism constant is incorrect, then each line will have the same exact amount of error present regardless of its length. So one's an additive error, the other one is a multiplying error. It's a scaling error. Now, the problem with this is the scaling error won't always get picked up by a least squares adjustment. For example, this is another type of spreadsheet that I have that I use with my students is for adjusting a traverse. Here is a 4-sided traverse with the original azimuths and distances with a scale of 1. So these scale distances are the same. This is how this traverse closed, 1 in 18,145. Okay. Now let's assume that they had the wrong parts per million correction in for the distances. And what happened was that each one is off by a proportional amount. So let's say I scale each distance by 1.01. So each of the distances got longer. by proportional amount. But you look at what happened to my precision, it's the same exact thing. Why? Because the error of closure increased by the same amount that the perimeter did. So my relative error is still the same. So even though it's a multiplying error, because it affects all of them proportionately the same, it doesn't show up in the adjustment. However, if I add 5/100ths of a foot to each distance, okay, I change it by that amount, it does change the geometry of the overall network and my precision drops. So depending on if it's a scalar or a scaling error, it's going to have a different effect on it. But the point is I want to get rid of those systematic errors and not shove them through the adjustment in the first place. All right, now when we talk about redundancy, degrees of freedom, we have to kind of define it in terms of multiple unknowns now. Before, when we talked about redundancies, we talked about taking something and measuring it a bunch of times, and then every extra measurement was a redundancy that was in there. Now we're going to be dealing with networks where we have generally two or more unknown quantities in there. So in the case of my level circuit that I had two unknowns in there, the elevation of Q and the elevation of T. So N is equal to 2, number of unknowns. My number of measurements are 1, 2, 3, so I have 1 degree of freedom. That's what allows me to compute my misclosure down over here. If I didn't have this closing one here, I would have the same number of measurements as I did unknowns, and I would have a unique solution. Can't track down any errors or do any math checks. In my other network, where I put in these crosslinks in here, I had 5 measurements with the same two unknowns, and now I've got 3 degrees of freedom. This additional closing one plus these other 2 that I added into there. So I can see that every time I add a measurement to a set like that, I'm adding a redundancy. Now, the thing we got to be careful of is the measurements have to be independent measurements. That is, we can't just, like if we're measuring a distance with a tape, we can't just look at the tape, read it, glance away, glance down again and read it again and say that's a second measurement. We have to change something about the measurement condition to ensure that our systematic or mistakes aren't being repeated. And a real good example of this is if you don't balance your backside and foresight distances in leveling and you don't use a separate setup. So in a case like this where I'm going from A to B, I'm set up here on an unbalanced situation. And I don't know if there's a collimation error or not, but if I use an unbalanced backside and foresight, I'm going to have a potential error in B based on that systematic collimation error. Well, if I say, okay, well, I'm just going to leave the instrument there, then I'm going to turn around and I'm going to read a backside and a foresight to A, I haven't compensated for that systematic error that's there. That's that collimation error. I'll get a perfect closure. Look at the same readings going in one direction I did in the other direction. I'll say I got perfect closures. There's no random errors in there. That doesn't work that way. What we need to do is when we set up is we read our backside and foresight and use good field procedures to allow those errors to compensate. And then in between this and the run back, we disturb the instrument setup. Okay, we take it down, we re-level it, we set it back up again, make sure it's balanced, and then read our backsights and foresights again. So we don't repeat any measurements. We don't repeat the same errors in one run and then back on the other run. So these are what independent measurements are. Is we disturb something about the measurement condition, and it just could be just re-leveling the instrument, but we do it so that we can make sure that we're not repeating the same systematic errors and the same mistakes going in both directions. All right, in leveling, an observation between 2 points is considered the sum of the backsights or foresights between them. So if I'm trying to establish the elevation of point 2 from point 1, some of my backsights and some of my foresights represents that elevation difference going from here to here. I don't really care about the elevations of my turning points in between. I care about the elevation difference going from point 1 to point 2. So if I'm going to go from point bam dog to A to B, how many observations are needed to determine the elevations of point A and B? Well, we need a minimum of 2. But 2 doesn't give us any redundancy because we've got one measurement and one unknown, a second measurement, a second unknown, so we have a unique solution. So if we add, okay, so we're going to add a redundancy. So the question is where do we add a redundancy in order to make sure that we've got a redundant network? So if I had a third measurement, I'd go from B all the way back to benchmark dog. That gives me a third measurement with 2 unknowns. It gives me a degree of freedom of 1. Or I could go from A back to BM dog. I have 3 measurements. I have 2 degrees, 3 measurements, 2 unknowns, and 1 degree of freedom. Both of these networks have 1 degree of freedom. But these are true redundancies. This is pseudo redundancy. And by pseudo redundancy, what I mean is it's a redundant network, but there's one point in it that doesn't have redundant measurements into it. We have an unknown at point A and B. That's an elevation. That's a vertical. We have one unknown at each point. In order to have a redundancy, we have to have at least 2 measurements to resolve that unknown. So for A, we have redundancy, but for B, we don't. If there's a bust in a reading between A to B, we'll never know it. That won't affect the closing one here. So what we need to do is make sure that if we've got 1 unknown, we've got at least 2 observations into it. 3 gives us even more redundancies. For horizontal, it can get even more complicated because for horizontal, at each point, we have 2 unknowns. We have north and east coordinates unknown at each point. Now, in a traditional traverse, what we do is we measure all the interior angles. I'm dating myself here because that's what we're doing, the old traditional point by point. And then we measure each side, okay? Angle, side, angle. And what we normally do to adjust this is we fix the coordinates of one point and we fix the direction of a line. So we'll say, we'll assume this direction is south 10 degrees east. So these coordinates are 10,000, 10,000. And that means that we now don't have an unknown here. Those go away. Those are fixed. And we have 2, 4, 6 unknowns now because there's 2 unknowns at each one. So we have 8 measurements, 4 angles, 4 distances. We have 6 unknowns. It gives us 2 redundancies. And we normally have 2 redundancies because if we do this in the classic sense, we compute latitudes and departures. How do we check for closure? We add up our latitudes to see if they equal 0, and we add up our departures to equal if they equal 0. Those are our 2 degrees of freedom. That's where our 2 math checks come from. If you're missing any of those, then you don't have the ability to close it. You have that open traverse, you do the forced closure and that type of thing, which assumes there aren't any errors. Now, we can add redundancies doing it different ways, and sort of like we did with the level circuit. We can do cross ties for a brace quadrilateral. That gives us 2 more distance measurements to get 4 degrees of freedom. We could shoot distances in both directions. Okay, so when we're measuring this angle here, we can shoot the distance in both directions. So now we've got 12 measurements because we have 8 distances and 4 angles, and we've got 6 degrees of freedom. If we shot the direct distance in both directions, we'd have 8 measurements. We have 6 unknowns. We have 2 degrees of freedom. But do we really? If you think of the traverse as a structure, what we want to do is we want to add rigidity to that structure by the way we measure things. So we know that if we're going to, a braced quadrilateral is a nice strong structure because that puts members across that structure so that the points aren't as likely to deflect as much. If I just measure distances, however, and I don't have the angles measured, I can really skew this thing here. So even though I've got 2 degrees of freedom, there's pseudo degrees of freedom. They're not real degrees of freedom because they don't fix these points here because they deflect very easily. So we have to add an angle in here, or we have to add a cross distance. If we put a cross distance in here, then that would add some structural stability to that traverse. Okay, so we got to be careful about when we talk about adding redundancies, what kind of redundancies are we adding, or were we adding them? Okay, one of the advantages we said that we can have with least squares adjustment is weights. We can throw weights on things, and we saw that one of the weighting strategies we used in last week's example was, I think, the different types of precisions that were used for the distances and that type of thing. But for weights in vertical and horizontal networks, there are other ways that we can look at how we weight those things or give quality to the type of stuff. One way, and I didn't address this specifically here, but it's say if you've got somebody that's doing a 3-wire level network and somebody that's doing differential leveling, you tie them all together, you know, the 3-wire leveling is going to be a higher accuracy or a better set of elevation differences than differential is. But let's say that we're using the same measuring techniques. Say we're doing differential leveling throughout the entire area, and we still want to take into account weights. Well, there are two things that we can look at that affect the quality of the measurements. One is if we're going from J to K is the number of setups that we have, because every time we set up the instrument, we introduce the potential for an error. So whenever we set, we might have 3 setups here, we only have 2 setups here. This one's going to be subject to more error than is this one right here. So our weight could be inversely proportional to the number of setups that we have. So 1/3 versus 1/2 here. This is a higher weighted situation than this one is. The other one could be based on distances, where we expect more error to accumulate along this long distance than we do along this short distance. So we could make the weight inversely proportional to the distance, so that the longer distance is going to have a lower weight than the shorter distances. So those are 2 primary weighting criteria that we use for leveling. Pretty simple and straightforward for differential leveling. For distance, for horizontal networks, the 2 types of measurements that we're dealing with are angles and distances. So what we use for angle and distance weighting is the stuff we talked about before. The error that we expect in the distance based on the manufacturer's stated accuracy of the distance measurement, the total station centering error, and a reflecting centering error. With angles and directions, again, it's centering errors, distances that we're shooting, and the specifications for the instrument. And you'll see that when you work with least square software, you're always inputting stuff like that as part of your network adjustment. And you very rarely should never put in zeros for these things here, because you're assuming there's no error in them. You got to put in reasonable errors for them. But that's basically what the weights are: 1 over the standard deviation squared or 1 over the error squared, the expected error in that. So those are the weighting criteria. All right. So let's look at how we actually do a least squares adjustment. We'll do this longhand here on a simple network, just to give you an appreciation for the calculations that are involved here. Least squares minimizes the sum of the squares of the residuals of the observations. Each observation, each measurement is going to have a residual associated with it, because if everything fit perfectly, there'd be no errors, there'd be no residuals, that type of thing. In a vertical situation, we're running a level circuit, the unknowns are elevations. And the measurements are simple addition and subtraction. This is how we determine what our relationship is going from one point to another point. So we take the point that we're coming from, add to it the back site reading, subtract to it the foresight reading. That's as difficult as the math gets for doing a differential leveling circuit. And because that math is simple, the least squares adjustment is a direct solution of simultaneous equations. It's pretty straightforward. You just put all the numbers in, do your calculation, and bang, you get your adjusted elevations. Easier said than done. All right, let's look at, we'll do this with the network that we had, 4 observations and 2 unknowns. Good. So in order to minimize the sum of the squares, the sum of the residual squared, we have to create an equation for each measurement that includes a residual term. So if we look at it this way, we say, well, how do we get from here to here? Well, the elevation of Q is equal to the elevation of BMA plus this elevation difference here to get that. Plus there's going to be a residual term in there for some uncertainty in it. So that's our observation equation going from here to here. To get to point T for our next one, we go from this elevation, we add this to it to get that elevation, and we add its residual term, and so on and so forth. So each one of these, we write an equation. Right? Now, some of those numbers we know, some of those numbers we don't know. The numbers we don't know are the elevations, are the points that we're trying to determine, and also the residual terms. Right? So now, because we're going to minimize the sum of the squares of the residuals, what we're going to do is we're going to rewrite these equations in terms of the residuals. So we just solve this equation for VQ. So that's equal to this right here. This is equal to this right here. This one's equal to this right here. And this one's equal to that one right there. Just rearrange them. So now all we got to do is square each one of these, add them together, and minimize that sum. So here's our equation. Okay, our function, sum of the squares of the residuals is first residual squared plus the second residual squared plus the third residual squared plus the fourth residual squared. See that? We have 4 residuals because we have 4 observations. And in some of these, the elevation of Q appears. In some of these, the elevation of T appears. And in some, elevation of T and Q appear where they're connected. Okay? So now all we got to do is minimize this thing here. Now, the way we minimize a function is by taking its first derivative and setting it equal to 0. This is where we get into the calculus side of things, right? So we take the partial derivative of this function with respect to each unknown and set it equal to 0. So we're going to take the partial derivative of this with respect to the elevation of Q, partial derivative of this with respect to the elevation of T, and set both of them equal to 0. So if we do that, and I skipped a bunch of steps in here. If you want, I can put them all up for you on the internet. You can look through them, all that kind of stuff. I do have ones worked out on my website and that type of thing. But basically, the partial derivative, the derivative of that function with respect to the elevation of Q, you wind up with this equation right here. 3 times the elevation of Q minus the elevation of T minus 1623.92 is equal to 0. You wind up with this equation when you take it with respect to T. 2 times the elevation of T minus the elevation of Q minus 829.818 is equal to 0. What we have here now are 2 equations and 2 unknowns. So basically we just set one equal to the other and solve, or there's different ways we can solve it. We can take the elevation of T, solve this equation for the elevation of T and substitute that in here. But regardless, 2 equations and 2 unknowns, we can compute the elevation of those 2 points. Those 2 elevations are the ones that minimize the sum of the squares of the residuals. And because it's leveling and it's simple addition and subtraction in here, once we set this up, take the partial derivatives and set these 2 equations equal to each other, it gives us those elevations directly. If we added another observation in here, that one from BMA to T, we add another residual term in here. 820, which one is it? Where'd I put it? 822.34 minus elevation of T when I take into account this stuff here. This plus this minus elevation of T to get that residual. So I put that on there, and now when I take the partial derivatives, I'll have another term for T. I will not have another term for Q because Q doesn't appear in this residual here. So every time I add one, I just add another residual term onto that equation, and I take the partial derivative of it. All right. Now for horizontal is a nonlinear situation because we have 2 unknowns at each point. And when we determine the unknowns, when we determined elevations of those points, all we did is we added and subtracted. But if you're going to determine coordinates of point B from point A, you're going to use a direction and you're going to use a distance, and you're going to take sine and cosine. So you're going to bring in trig into this. So we don't have a linear relationship between these 2 points here. We don't have a linear relationship between these 2 points here. We have to take that stuff into account. So the way, when you work with complex equations like that, to take a partial derivative of an equation like that and set it equal to 0 to minimize, you basically have to take the first derivative of it, plus the second derivative of it, plus a third derivative, and so on and so forth to infinity. And you set that equal to 0 and then solve it, and then you can get what the unknown is. Well, taking them all to infinity, for one thing, you don't have the luxury of time to do that. And secondly, usually after that first term, it starts to drop off and those subsequent terms become smaller and smaller. So what we do is we use what's called a Taylor series or Taylor approximation, which says that we'll just take the first derivative of it And that'll give us an if we use an approximation in that first derivative, that'll give us a correction to that approximation. Then we apply that correction to the approximation, resolve it again, and keep on doing that until our corrections get small enough that we don't have to go below some acceptable level for us. Like if we're computing coordinates, we may say that, well, when it drops down to where the correction is less than 1,000th of a foot, we don't have to worry about it anymore because that's within what our uncertainty is, okay? So how does this come into play? How does this get a little bit more complex than our level network? Well, our distances, when we have a distance relationship between an at point and a 2 point, we have our measured distance, that distance that we measure from A to T. But then what we need to do is figure out the residual based on what our initial approximations are for the coordinates of these points, and we compute the distance from those initial approximations. The difference between the measured and the one that's computed for initial approximations is our residual. Now, when we look at this, we see that we've got a squared term here, and a square root term outside here. So we have to take the partial derivative of this function with respect to each of the unknowns. And there are 4 unknowns in here: the north and east coordinate of the 2 point, the north and the east coordinate of the at point. So here we have our 4 partial derivatives. And in this one case here, they have the correction that's applied to the initial approximation. So for example, if I was just working with this one distance, and I had initial approximations at both ends, I would compute what my corrections are here based on some initial approximations. Then I would take those corrections, apply them to the coordinates, recompute these to get new updates. If they're still too large, then I would keep on going. So I would iterate through the process. That's why you'll see in most adjustment software, one of the things that it tells you when it's done computing or adjusting a network is it says it converged in 3 iterations. That's what it means, that it's come down to its tolerance level within 3 runs through the network. Okay. Now that's just for one distance, and that's just for distances. Here we come with our good friend, the angles again. When we're dealing with angles, things get real complex real fast. With angles, we've got 3 points that are involved: the at point, the from point, and the 2 point. We have the measured angle out in the field, and then we had the angle that's computed from the coordinates. Now in this case here, we're looking at the computed angle between these as being a difference between from the azimuth to the 2 point minus the azimuth to the from point. Now, those are computed based on coordinate differences and the inverse tangent function. Now, the thing we gotta be careful of is both of these are in the same quadrant. So this works fine the way it is. If this line were in this quadrant here, then we would have to correct its azimuth by adding 180 degrees to it or subtracting it from 180 degrees. If it was in this quadrant, then we have to take into account 360 degrees. So in addition to the fact that we're dealing with coordinates and tangent functions, we also have to look at which quadrant we're in and make sure that we're always taking the 2 minus the from so that we get the clockwise angle. Otherwise, we'll get the angle to the left, and that throws a wrench into everything. Okay. So now we take the partial derivative of this guy with respect to each of those unknowns, and there now are 6 unknowns. The north and east coordinate of the at point, the north and east coordinate of the from point, and the north and east coordinate of the 2 point. And we see that the at point, its partial derivative is got both terms in there because it's tied to both the from and the 2 points, whereas the from point's only got 1 because it's tied to just the at point, and the 2 point's only got 1 because it's tied to the at point. So same thing. I start with my initial approximations for those coordinates. I solve this here to get my residual. I come into here and I figure out what are my corrections. I update my coordinates by that, and then I check it again to see what my residual is and see what my corrections are. So it's a big iterative process. Now, if I mix it together and say, okay, not only do I have a length, angle here, but also distances, Now we've got a connection of all those different things. So this line here is subject to both the angular residual, but also subject to a distance residual. So it becomes really complicated really fast, which is why I don't have a manual calculation for it here, but I do have them on the website. If you look at my least squares light topic on my website, if you want to really get into the calculus and stuff. All right. So now when we look at this and we look at networks that we can have, one of the things that we can do is we can have a traditional traverse. When we talked about this before, we have 4 angles and 4 distances, or we can have a trilateration network where it's got just distances. Trilateration network, we don't have to horse around with this guy right here. We just deal with this thing right here. If we have a triangulation network, which was the popular one to do before EDMs came along, is you're basically having angles all over the place, but you have to have at least one baseline that's measured, okay, in order to propagate solve other triangles and stuff in there. Or you could have a combined network where you mix a bunch of angles and a bunch of distances together and then do it that way. Now, I had a question on there about the Crandall method, and I didn't specifically talk about that as a simplified adjustment method. A Crandall method is a pseudo least squares method for traverse adjustment. What it does is it applies least squares adjustment to the distances only, but not the angles. And that's because that's easier to do because you only have these 4 to work with, as opposed to the angle where you got all 6 of them to work with. So a Crandall method, which is in most adjustment software, is really a pseudo adjustment, a pseudo least squares adjustment. It only does it to the distances, not to the angles. I'm gonna get a breather here. Okay. We talked about adjustment statistics, and this is where you can get overloaded on stuff real quickly. The standard deviation of the unit weight is an indicator of the overall adjustment statistics. So when you adjust something and you make decisions about what are my centering errors, what's my manufacturer's specified accuracy for the instrument angle measurement, the distance measurement, or for my total state, or for my GPS, the MSA for the horizontal vertical accuracies. Also, what kind of weighting criteria that I use, all that has to come together to give me something that makes sense in the end. If I make my weights too loose, that allows my points to move too much, and it's not representative of the quality of my measurements. If I use very high weights, what that does, it restricts the movement of my individual points to adjust, and it gives me a false sense of security because then I've got small standard deviations on things. Well, the standard deviation of the unit weight is one indicator that we can get coming out of there that tells us how good is the overall adjustment. And by definition, unit weight means 1. Standard deviation unit weight should come out to be equal to 1 as a combination of all the different types of measurements we mix together. There's also another test that most software applies, which is called the chi-squared test, or a student t-test, which is also another measure of statistical significance, but that's one that gives you an overall assessment of the quality of the network, not necessarily the individual ones, but of the overall network. For the individual points, now that we've adjusted, say it's elevations or horizontal coordinates, now we want to have something that we know about the quality of those adjusted quantities. And we added up a bunch of numbers together before for our measurement, and we computed the standard deviation of it and the error, the most probable value. Those were our indicators for a measurement of a particular thing. In a least squares adjustment, when we do a elevation adjustment, or vertical adjustment, we wind up with an adjusted elevation and we wind up with a standard deviation of it. That basically is the same thing as what we had when we dealt with a measurement of an object, is we had the standard deviation gave you 68% of the area underneath the curve, or it gave you the 68% confidence interval. If we wanted to have the 95 confidence interval, then we multiplied it by 1.966, like we did before. So it's basically the same thing as we had before, because it's only acting in one direction, vertical. When we get to horizontal, however, we can't separate the north component from the east component, because the same measurements are used to generate both coordinates. When we determine a latitude or a departure of a line, it's a function of the same length in the same direction. So there's a relationship between those two. So while we might have a northing uncertainty, say we've got our standard deviation for our northing coordinate, and we have a standard deviation for our easting coordinate, they're not really independent. So if we combine these two graphs together, we have what's called a bivariate distribution. That is, they're normal distributions, but they're a function that are related to each other. So if you kind of squint and look at this in 3 dimensions, you've got one distribution in the north-south direction, and another one in the east-west direction. And here's our standard deviations for those guys right there. If I were to look at that in a plan view now, here's my adjusted point with its best representation of its position. There's a standard deviation east in the easting coordinate, the standard deviation in the northing coordinate, and I can create around it what's called an error rectangle. Okay. Now, an error rectangle is just kind of like the worst case scenario. It's the biggest type of thing. The standard error ellipse is the one that is tangent to all sides of that error box, that error rectangle. And there's an infinite number of them that will meet that condition, but it's the one that maximizes the length of the semi-major axis and minimizes the length of the semi-minor axis. And what that tells us, the standard error ellipse tells us, is the position is weakest in this direction here, at this azimuth to the semi-major axis, and is strongest in this one right here. And when we plot error ellipses, we can kind of look at the way our measurements were made and kind of predict how they're going to behave. So think of it sort of like the movement of a joint of a structure. Okay. If we look at, now here's my 3-dimensional bivariate distribution. Here's that standard error ellipse. Now, where the plus or minus standard deviation indicated 68% of the area underneath the normal distribution curve, the standard error ellipse, because it's a bivariate, represents about 30 to 35% of the area underneath that combined 3-dimensional curve. Okay. If we want to increase our confidence, we can't just multiply it by a single number like we could with a single variate distribution, because it's bivariate in its behavior. We have to take into account the number of degrees of freedom that are part of the adjustment, that type of thing. So in a case, and that requires use of the F statistic. The F statistic, in most statistics tables will have this, and adjustment textbooks will have this. It'll have the F statistic, which is a multiplier based on the number of degrees of freedom and the confidence interval. So for instance, a typical setup is for a confidence interval of 95%. The F statistic for 1 degree freedom is 199.5. For 2 degrees of freedom, it's 19.039.55. You can see it drops off very quickly here, so that the standard deviation, or the size of an error ellipse axis, semi-major, semi-minor, is equal to the standard one times 2 times the square root, 2 times the F statistic. So if I wanted to have, if I only had 1 degree of freedom in my network, and I want to have a 95% confidence interval, it would be 199.5 times 2, take the square root of that, which is going to be still a huge number, times S. So you can see that my 95% confidence interval is going to be relatively large. I just knocked down my tree. I got too excited here. If I go with 2 degrees of freedom, I decreased my confidence interval spread substantially for that 95%. So you can see that's that effect of random errors, right? So now, bring this all together. Anyway, bring this all together. When we look at, this is an actual, I ran an adjustment on a simple traverse. And what I did is I held a point fixed, and I put in bearings, put in angles and distances, and I ran an adjustment on it. And these are my error ellipses, my 95% confidence interval error ellipses. And they're multiplied 100 times so that you can see them. Otherwise, you wouldn't be able to see them because they're relatively small. So if you look at the behavior, the further I get away from where my control point is, the more the ellipse is oriented perpendicular to a line from there. And that's what I expect. I expect my deflection to be perpendicular to the line from my control point and constrained more in that direction from the control point. And if I see what's happening here, same type of thing here. Over here, because I haven't gone very far yet, it's pretty circular in that context right there. All right, so what is this leading up to? Well, so say a surveyor did this survey here, lot number 3, and a surveyor came over and did lot number 4 next door. And he did his angle measurements and distances. He held this point fixed. It really doesn't matter which one we hold fixed. And we plot his traverse and adjusted coordinates and his error ellipses on top of ours. And what we see here is the same type of behavior. Radial here, it's perpendicular to that. Radial here, perpendicular. And once we get way out over here, here's this error ellipse over here overlapping on our error ellipse right in here. So basically, this is saying here, when I look at that, if I magnify those two error ellipses, the semi-major axis for lot number 3, this thing right here from here to here is 0.8 feet. Semi-minor is 0.4 feet. For the northeast, that's 0.9 feet and 0.3 feet. So that's a pretty good chunk of distance. Now, if I look at it even closer, I isolated those two and I looked at the overlap area. The overlap area between those constitutes half a square foot. I mean, well, half a square foot, that's not very much. No, it's not. But when you look at, it's roughly 0.6 feet by 0.8 feet. Well, what does that tell me? Well, see these monument nests here? Most of these guys are within that overlap area of the two error ellipses. So what that tells me is there's no statistical difference between any of those points, especially this one right here, okay, where somebody insisted on putting a monument right next to the other one. To me, those are right in on top of each other in here. There's no statistical significance between those two outside of the fact that we want to be able to slap something else in the ground that shows that we were there. But statistically speaking, it's the same thing. Look at these two. They're less than 0.2 of a foot apart. And that falls well within the error ellipses here. Okay? So we got to kind of look at what do those monument nests really mean from a numeric viewpoint. Now, there's other reasons we can wind up with monument nests and that type of thing. But if it's strictly because I got a slightly different position because of my survey quality than somebody else did, then is it really statistically significant that there is a difference between where that monument is and where I propose to put a monument? The other place where it comes into play, and unfortunately I see this too often, and I use this example when I talked about the rules of construction, is you wind up with numbers that come out of an adjustment that really don't mean anything. They're within the noise level of the adjustment. So when I've got a distance of 0.3 feet, I mean, if that's within this area here, that's great. That's within the uncertainty of both of those surveys and stuff. So that's zero as far as I'm concerned. That doesn't exist. And that 0.01 feet definitely doesn't exist, let alone the fact that if you ever tried to measure 0.01 feet at a particular bearing with a total station or whatever, that's a heck of a challenge. Okay, try that. That'll be your other homework assignment for this weekend, is go out there, lay out a 0.01 foot line at a specific bearing. So when we look at the statistics, we got to look at the statistics not only just as a numeric thing, but what do they mean physically on the ground? How do we connect what we've been measuring on the ground with what our analysis tells us, and what our analysis tells us with what we've got on the ground? Okay. All right. So that is a quick trip through measurement and computation errors, starting with numbers as communication and working our way through where errors come from, how they behave, how they propagate, and a very, very cursory introduction to least squares adjustment and that type of thing. And I'll admit right off the top of my, that's a whole lot of stuff, right? The least squares alone is a semester-long 3-credit course to be able to get a hold of all that kind of stuff, in addition to some of the advanced type of topics that are involved. But basically, when you've got statistics coming out of your adjustment, at least maybe now you have a little bit of appreciation for where that stuff comes from and what that means on the ground with respect to that stuff. Okay. Are there any questions on any of this? Let me see.
There's a couple of good things in the chat, but so one that's on a private one that's on a private one is, after this whole presentation, how much is the difference in setup errors between a 1 second, a 3 second, and a 5 second instrument?
The setup errors don't matter. But I tell you what, if you look at that spreadsheet and you just leave the setup and the centering errors and all that kind of stuff the same, and just change the DIN specs for the instrument, and their number of direct and reverse, that'll give you an idea for how the different resolution of equipment will have an effect on it.
There you go.
But be realistic with the setup errors and that type of thing. Don't just assume they're zero, because they're not. There's going to be errors with respect to that.
Yeah. Danny has his hand up. So.
Yeah. Question.
Hey, Jerry. So I was wondering, I saw the picture of the pin cushions. Was that something that you discovered, or where did you get that picture, man? That's pretty gnarly.
I've gotten these from different places. A couple of them I come across, and I've had surveyors submit them to me after I talk about these types of things, and whether it's illegal or if you ever run across some weird stuff like this, or just please send them to me. I kind of collect these things.
I have one that I found not too long ago of 2 monuments that were set within a tenth of each other by the same surveyor. I don't know how that happened, but it blew my mind. Maybe
he figured he got better over the years. Somebody had, I don't have this picture, but somebody had, I think it was John Ellingson, our former state geodetic advisor, 2 NGS control points that were set on top of each other. I mean, they were like, literally, it was one disk that was overlapping another disk, so I thought even the NGS isn't immune from that type of stuff.
Well, the profile picture for Mentoring Mondays on Facebook is a pin cushion between the BLM and the Forest Service. So
that's understandable. That's the interagency competition,
And then
if you're going to wind up the same answer, they're going to cut somebody's funding, right?
I've seen monumentation set to replace a section corner and numerous quarter corners that the brass cap monument was within a foot and sticking up 0.8 of a foot above existing grade, and it cost me to wait to do my survey probably 8 months while the other surveyor redid his to make it right, after I gave him the correct positions of the corners.
Well, one of the other thing that kind of gets me on this is some of those pincushion type of things is when you're chasing around all that stuff, it not only is not statistically significant, but if that's a monument, a PLS monument that was originally set at an accuracy of what it was, and then you're looking at all the evidence that you're trying to evaluate now, and it doesn't point to a unique location, there's going to be uncertainty in that position to begin with. So why bother popping another monument in? Somebody asked a question about any good book that you could recommend that covers these materials. The best book out there is Adjustment Computations by Galani, Spatial Analysis. And what I suggest you do, it's an expensive book. And if you look at my profile on my website, you'll see what my stand is on textbooks and that type of thing. What I suggest you do is you look at like American Book Exchange or something, or one of the used book sites, and look for a slightly older edition. I think the 6th edition is the current one, and I've got the 4th edition, and it's essentially the same. So you can pick that up, and it's not really easy reading, because he does go through all the derivations of stuff. But it's about the best book out there for that type of stuff. And if you do have any access to software that's got least squares in it, whether you're dealing with StarNet or Traverse PC now has got more least squares capabilities in it and that type of thing. you can use that along with the examples in the book here. And he does have free adjustment software that you can download that you can try out different things with it. So, but that's the best book that's out there. I mean, that's primarily the only book that's out there that really addresses this to any great detail. Oh, one other thing I was going to mention is somebody said, now I know what the error ellipses in Traverse PCR. Remember, there are also relative error ellipses. Error ellipses are for the points themselves. Relative error ellipses are for the lines connecting the points. So there's uncertainty in those lines also, as well as in the points that connect them. So you can have relative error ellipses between points as well as at the points too. So that's what I'm saying is with statistics overload, it's really easy to happen with all that stuff. Okay.
I just threw in the chat the link to Amazon for the book. It's actually it's only $46 on
For which edition? For the 5th edition?
the 6th edition. Oh, that's a rent. Okay, so buy now, 150 on
Yeah, look for like the 5th edition. Like it's essentially the
Yeah.
same thing.
Yeah.
Oh, maybe some corrections or some additions in there, but it goes up to the GPS type of stuff too. So, all right. Any other questions, comments? Yeah, CMM. I used to play around. As a matter of fact, I did an evaluation of the CMM back about 20 years ago or so with the Denver office and stuff. And yeah, I played around with it. That's pretty good. See what else is out there. Michael, the StarNet. Most of the GPS adjustment software is going to have its own least squares adjustment, and that you can integrate other measurements with it, not just GPS, but you can bring in total station level circuits and that type of thing. All right. But it's, the key to all that stuff is being sure that you're setting up all of your instrument setup errors correctly in there so that it propagates those errors through there. All right, I'll just burn through some questions. I'm not going to go through the entire assignment here, but I will post the answers up on my website later. I'm going to just go through a couple of these things here. All right, now indicate whether the following are random or systematic errors. Okay, number 6, manufacturers specify RTK GPS horizontal accuracy of 10 millimeters plus 1 part per million. Is that a random error or is that a systematic error? Anybody want to guess on that?
I'm going to say systematic error.
Yeah.
Yeah, that's a safe bet, but it's not. It's a random error.
What?
Now, remember, it's plus or minus the constant plus the parts per million. That's a random error. Okay, just like the DIN specifications for the angular error for total stations is a random error. Sticking compensator and automatic level. What's that? Random or systematic?
Yeah.
sticking commentator. I have to say random because it's not.
Yeah,
really
that's
broke-
random.
It's not broke
Yeah,
all the time.
That's random. Yeah. Even though it's an instrument maladjustment, it behaves randomly unless it's totally stuck, in which case
Oh.
it's a mistake to use it. So, okay. All right. And then I mentioned the Crandall Traverse adjustment method just now, but that's basically what this is in here is it's a least squares adjustment to just distances. What are the 3 sources of errors?
Random, systematic, and then what was the 4th or the 3rd one?
Well, see, that's when I get the students on that all the time too. Those are the behavior. Those are types of errors.
That's the behavior.
Sources are where they come from.
Okay.
Sources are the environment within which we make our measurements, the equipment with which we make our measurements, and the people that are making the measurements. Those are where the errors come from. How they behave are random, systematic, mistake, and that type of thing.
Nice. Very good.
All right. I talked about that one. Well, let me skip over here. Okay, as a joke, question number 3. The new rod person was given a level rod that had the bottom half foot cut off. If it was used for all the backside and foresights on a level loop, what would it affect the level loop closure? Why or why not?
No. No.
I know you want to say no, because you figure it's a trick question, But the question is
Damn.
why would it be no? Because if it's got a 1 foot cutoff, that means your rod readings are all going to be 1 foot too high, right? So if it's 1 foot too high on the back side, 1 foot too high on the foresight, what happens to that 1 foot error? It's added in one case, subtracted in the other, and what happens? It goes away.
Yeah.
Right?
Yeah.
So that won't affect the level of disclosure. Okay, even though the bottom foot of that's missing, it won't affect the level of misclosure. Okay. Let's see. I'm gonna skip that one. I'm gonna skip that one. All right, did anybody do this one? This was a diagram of a level circuit where benchmark Q or where point Q was tied to 4 benchmarks. And we want to know what the most probable elevation of point Q is. Anybody do that one? Anybody figure out how to do that?
Oh,
And I said, well, now knowing what we know now, we'd write an equation with a residual for each one. We get 4 equations with residuals. We'd square them. We take partial derivatives of them, set them equal to 0. Well, in this case, you don't have to do that. Okay. Because that one point by itself is connected to 4 elevations. All you got to do is compute the elevation from each of those 4 points, get 4 elevations, divide it by 4, and get the average that way. See that? That's what I call the brute force method on my website. Is basically compute the elevation from here, from here, from here, and from here. You get 4 different elevations. Take the average of those 4, and that's going to be your most probable value for that, most probable elevation for that point. Now, if it was tied to point Q, that'd be a different story. You couldn't just do it that way. All right, that's it. I'll put up the other answers later on. Let me stop screen sharing. And I think I already got the link up there to my I'm not picture. I've got the link up there to that spreadsheet, and I'll incorporate the one for the vertical for the GPS in there also. Yeah.
Pretty cool.
All right. Anything else?
Anybody got anything else they want to add?
no. Thank you, Jerry.
That was
You're
awesome.
welcome.
Yep.
Hey, I put a link in the chat to videos that go along with that textbook.
Okay,
Oh,
good.
nice.
They
Good.
walk through the chapters. I found it really helpful.
Good.
Still
Good.
didn't really understand everything he was talking about, so this is really
Well, yeah,
nice.
and I have you see, he's in his textbook, he tries to cover every single base that there is. And I just touched on the real basic stuff here. So once you start working with multiple measurements and that type of thing, GPS, traditional, all this kind of stuff, it can get really hairy really quickly, which is why we like software. But conceptually, if you just kind of keep track of what he's talking about in a concept wise, I think you should be okay.
Hey, Jen, on that link, do you think I can throw that on this session's page without any issues?
I don't see why not. It's just on their on the publisher's website.
Oh, it's right from the publisher.
It's not
Okay.
behind a code or anything. You don't need
Yep.
like a scratch off code.
Okay.
Yeah.
No, if it's coming from the publisher's website, we'll be fine.
Yep.
All right. Cool. Perfect.
That's why I put the link there, because I
Yeah.
thought,
Yeah. I love it. Thanks. Thanks.
yay
Nick.
for videos.
Exactly.
Yeah, and the link for the software should be up around somewhere around there also.
On the Wiley website. Yeah. Okay.
Yeah, it's called, I think the software's called, let's see, do I have? Oh, hell, I don't have it here off the top of my head, but it's like Adjust, I think is the name of the software.
Okay. I'll do some digging into it. I'll throw it all up on the page website.
Yep.
Sweet. Thank you,
All
Jerry.
right.
That
You're
was awesome.
welcome. If everybody's got any questions, feel free to give me a call, email, whatever. I'm just sitting here in my basement.
Hey, Trent,
Yes, sir.
how many, I know there's not a lot of people on this one that are in Nevada, but I'm sure a lot of these people would enjoy the current version of the Traverse if you could figure out a way to send it to them.
Oh, yeah.
At least online.
I think I threw it in the week 55 follow-up. I did throw the Traverse in there. So, yep. But I'll do it again. Yeah.
Great job.
Thank you, sir. Sweet. All right, everybody. I appreciate it.
Thanks for
Have a good-
coming,
Have a
everybody.
good night. Have a good day, Peter.
Peace out.
Bye.